Hi there, and welcome to Telefunken. Today's video is one in a series on the vintage Roland CR-78 analog drum machine. In this episode, we'll be calibrating the CR-78 to make sure it sounds like it was supposed to the day it left the factory. If you have a CR-78 that sounds a little off, or if you'd just like to learn more about what a CR-78 is capable of, then this video is for you. Before we start, we're going to need to make sure we have a functioning CR-78. That's to say, we need to be able to trigger the sounds and have them present at the instrument output. If your CR-78 isn't working properly, you may get some hints as to what's going on inside from some of the other videos in the series, introducing the CR-78, rebuilding the CR-78 power supply, and rebuilding the CR-78 logic board. We'll need a normally open, momentarily closed switch to trigger the machine, and this will need to be connected to a 1/4-inch jack. The type that might be used as a sustain pedal for a keyboard should do the trick if you happen to have one lying around. We'll also need an oscilloscope. While many electronic instruments can be calibrated using frequency counters, such as those built into some of the more advanced digital multimeters, in this case, we'll need to examine the waveform of each voice to determine the frequency, peak amplitude, and the decay time. A digital oscilloscope is handy, but not necessary. We'll also need a copy of the service manual for the CR-78, which is widely available on the internet. I've reproduced most of the relevant sections here in this video, but you really should have a copy of the service manual on hand. Calibration of the CR-78 proceeds in 3 steps. First, we set the tempo clock frequency, and then dial in the fade times. This is followed by the juicy bit, the calibration of each individual instrument voice. Not all of the voice parameters are adjustable, however. Those that are non-adjustable are indicated by a dash in the table on page 15 of the service manual. By way of example, the bass drum or kick circuit on the CR-78, shown here, allows for adjustment of both the voice frequency and decay via 2 independent trim potentiometers located on the voice PCB. The amplitude of the kick is non-adjustable, as indicated by the dash in the table. We're expecting a signal with an amplitude of 0.4 volts peak to peak, and the manual advises that we just check the operation at this point. Notably, the relevant volume of the kick and the other bass-heavy drum sounds in the CR-78 can be adjusted from the front panel using the balance control fader as shown in the schematic. This differs from the snare circuit shown here. Unlike the relatively simple kick, consisting of a single oscillator, the snare is comprised of 2 elements, a noise signal derived from a circuit shared by the hi-hats, cymbals, maracas, tambourine, and guiro, and a ring oscillator with a circuit similar to that of the kick. The snare circuit has an independent trimmer for the voice amplitude, but does not allow for the adjustment of the snare frequency or the decay. In cases like this, all we can do is test the performance of the voice using the reference values listed in the service manual, but if something is widely out of spec, we need to analyze and understand the circuit to identify the suspect components, those that might have drifted in value or failed in such a way as to give us the observed results. A couple of examples are shown here, but this type of analysis and repair is beyond the scope of this video. Before we get started, I'll point out something in the service manual that I found slightly confusing, or at least a little ambiguous. When defining the decay times for each voice, we're to use the time at which the voice amplitude has decayed to 1/10 its original value. Initially, I mistakenly interpreted this diagram in the service manual as suggesting that the decay time is the time at which the voice has decayed to 1/10 of a volt, which is incorrect. So if you see me using this approach with some of the first few voices in the calibration, don't follow my lead, adjust the decay to 1/10 the original peak amplitude. I hope you find this video helpful and take great satisfaction in knowing that your CR-78 is working like it should. So without further ado, let's get started. The first step in the calibration of a CR-78 is to adjust the master oscillator frequency, or the so-called rhythm tempo as it's described in the CR-78 service manual. And in order to do this, we need to either attach an oscilloscope or a frequency counter to the collector of Q1 on the logic board. And Q1 is right over here. And you can see an oscilloscope probe which is actually attached to the leg of capacitor C120, which is attached to the collector, the middle pin on that transistor Q1. And that makes for a convenient attachment point. What we can see on the oscilloscope is a square wave. It's not a balanced square wave in that the positive period is much greater than the negative period, if you will. And we see a period of about 12 milliseconds, giving us a frequency of about 81 hertz. And we're to adjust this with the tempo knob in the fully clockwise position. And we adjust VR101, which is this trimmer potentiometer right here, for a 10 millisecond period or 100 hertz frequency. And so I'll just carefully insert my screwdriver here. It's just a little jeweler screwdriver. And this is, of course, easier said than done. There we go. And if I turn it counterclockwise, I'm reducing the period and thereby increasing the frequency. And you can see I've got really, frankly, exquisite control over this, given the multi-turn potentiometer. And I can dial it right into 10 milliseconds. There we are. 9.99, 10.000 milliseconds. How nice is that? And this is done without the machine running. This is just, again, the master oscillator clock frequency. So the next step is to adjust the tempo knob fully counterclockwise, thereby turning down the frequency of the master oscillator. And we can see, once we make some adjustments to our oscilloscope, that we have a period now of about 150 or so milliseconds. And what we're looking for is a period of 200 milliseconds and a frequency of 5 hertz. So we're going a little fast at the moment. And the way we adjust this is by adjusting VR102, which is the potentiometer closer to the CPU, but adjacent to 101. And if I turn this counterclockwise, I'm increasing the period and reducing the frequency. And this is a little bit more, shall we say, jittery, in that there's a bit more play in this circuit, because we're at the very lowest end of the tempo range. And so depending on where we are, we appear to be measuring slightly different. I'll change the oscilloscope settings here, and this seems to give us slightly better ability to measure the frequency. And I need to turn it counterclockwise to increase the period, which is only refreshed properly once every sweep. So there we are, 200.09 milliseconds, and giving us a frequency of about 5 hertz. And so that's the master oscillator frequency adjusted. Now the next step is to adjust the fade time. And this is to be done with the tempo fully clockwise. And we are to have the samba running. And so samba is the third pattern from the right-hand side on the bottom row. We can now hear it. And that sounds lovely, doesn't it? I'll just turn that down a little bit. And what we're to do is set the fade out to short, and depress start stop. And when the sound becomes inaudible, we are then to count how many times the tempo light flashes before it comes on steadily, as it has done. So how many cycles through in the fade time can we hear? Okay. So I counted 9 flashes after I lost the actual sound. So let's see if we can do this again. 8 that time. And so in order to adjust this, what we do is we adjust VR103 on this same board. And VR103 is way over here, quite close to the power transformer. And I'll just slightly move some of these cables, position the screwdriver. So I'll turn this a rotation or two counterclockwise and see what that does for us. I counted 9 that time. I'll turn another rotation and see if it continues to increase. I think it's increasing, so I'll turn it clockwise. Again, this is a multi-turn potentiometer, so I'm having to turn it a few times. 6 times. Five and a half times. That was about 4 or 5. And I'll turn it back just a little bit. Try it again. Yep, that's about right there. And so what kind of fades does this give us? Those are our long fades. So I think that'll work nicely. Again, long fade. Quite nice. And we go from here to adjusting the actual voice settings. And that will require access to the voice board on the other side of the instrument. So I'll be tipping it up on its side and or back for these next set of adjustments. So we are set up to begin calibration of the actual voices in the CR-78. And the way that this is described in the service manual is using the horizontal input as a trigger, and the vertical input is connected to various positions on the PCB. And because we have a computer-based oscilloscope that has the ability to auto trigger, we can disregard the horizontal input and just go for the vertical input, which in the first case we connect to pin 34 on VG11, which is the voice board. And pin 34 is one of these 4 pins right here. From this perspective, it's the one on the left closest to me, closest to the front of the instrument and closest to the center of the instrument. So we've connected to that where we can monitor the output of the instrument. And this output that we're monitoring is not sensitive to the volume control, so it doesn't matter where that is. And we set the voice, we select the voice by using the instrument selector, and currently it's on the bass drum. And we connect a foot switch to the right jack and tap it in order to sound the instrument. And so you can see and hear that if I simply press on this foot switch, that we activate the instrument. I've got it connected to a small benchtop amplifier here, and that's what we're listening to. It's not the greatest fidelity, but it's good enough for our purposes. So I'll set up the oscilloscope and trigger it. There we go. And we see that we have a sound that looks very much like the one in the service manual, where we have a period of 14.4 milliseconds, frequency of 64.9 hertz, and a given decay time and an amplitude. The amplitude peak to peak is about 0.66 volts, and this is somewhat greater than that which is represented in the service manual, which calls for 0.4 volts, and we'll visit that in a moment. But first of all, the first adjustment we would make is to adjust the frequency of the note. And it is currently a little sharp. It's about 65 hertz. whereas it could be around 62.5 hertz. And this is to be done with the balance control in the lowest position. Because we're upside down, that's the highest position. And we're to adjust VR57. And VR57 is actually this adjustment potentiometer right here. It's on the very right-hand side of the instrument when it's in this orientation. So this would be the potentiometer that we adjust to adjust the frequency of this note. And we're looking for 62.5 hertz. That's 66, 61, 66. Down, turning it slightly counterclockwise. And that seems to increase the frequency. And by turning it clockwise, I decrease the frequency. And I'm about 60.6, 62.2, 65.2, 62.8, 61.2. Going to try for a single capture. 61.5, 62.5. That's right around where we want to be in terms of the frequency of the kick. And now we're to look at the decay, and we're hoping for a 100 millisecond decay. And the way we adjust this is with VR58, and VR58 is right up here. It's the furthest to the right and the furthest to the back along the edge of the board. And the decay should be set at 100 milliseconds. And the way that that is qualified is by measuring the decay from the initiation of the sound until the point where the peak-to-peak magnitude falls below 1/10 of a volt or below 100 millivolts. And we can see currently on the oscilloscope that if we capture a single shot, we have the kick decay going below 50 millivolts on the positive side after about 75 or 80 milliseconds. And so we need to extend the decay of this drum. And so the way I'm going to do that is by adjusting this potentiometer. Just reset. I'm turning it a little clockwise. And that seems to shorten the decay. If I turn it counterclockwise, that extends the decay until it's actually oscillating. So we want to be very careful with that. Okay, where are we now in terms of our decay? We've extended it a little bit, but not a lot. Oh, there we go. Quite an extension. However, a bit too much. I have heard people extending the decay to about 200 milliseconds, but that would be a decay similar to what I've just done. Yeah, that's around 200 millisecond decay. And I think that's a little too beefy. And so we'll bring that back a little. That's not quite where we need to be. This would maybe benefit from a multi-turn potentiometer. And there we are. That's about exactly where we want to be, around 100 milliseconds. So that did require some adjusting. We were far too short. And that's a much healthier kick sound than what we had previously, which was somewhat anemic. The next voice that we want to adjust is the snare drum. And here we're looking for about a 340 hertz signal. And what we're measuring is mostly the noise signal, I believe, because we've got about 2.8 kilohertz. This is not adjustable. The frequency is not adjustable. So we take it or leave it. We do have the ability through VR61 to adjust the amplitude. And if we compare it to the kick, it's about right. It's about where it needs to be. The next adjustment we're looking for is the rim shot. What we're hoping for is about a 1480 hertz signal, and I'll just zoom in on the time scale here. So we have a 1.8 kilohertz signal. So it's pitched a little high. Again, this is non-adjustable, and we're looking for about a 5 millisecond decay time on this. And I would suggest that we have slightly less decay than we want. We've actually got decay that is closer to 2.5 milliseconds. So the next instruments are the hi-hat, cymbal, and so on. And we're to move the balance knob to the highest position for this. And we're looking at the decay time, for example, for the hi-hat, which should be around 60 milliseconds. So let's look at that first. And we come back to adjust our time base. We see that we have a slightly shorter decay than we might prefer. We have 55, I'd say roughly around 48 or so millisecond decay instead of a 60 millisecond, but this is non-adjustable. We go on to the cymbal, and we're looking for about a 350 millisecond decay here. There we are. There's just so much noise in there, it doesn't know what to do with it. We have some very high frequency noise, and that's what is showing up on our oscilloscope here. And we're looking at a sound that decays below 100, 1/10 of a volt peak to peak by around 325 milliseconds. So this is approximately correct. And again, we have the ability using VR60 to adjust the amplitude here, but we'll leave it alone for the moment. Now we'll go to the next voice, which I believe is supposed to be a maraca. And it is supposed to have both a very short duration and similar pitch. So its frequency is about 1.1 K, and the decay time is supposed to be 20 milliseconds. I would say it's closer to 15. So the next is the clave, and the clave is supposed to have a frequency of 2.6 K, and it's 2.3 K. Yeah, about 2.3 K. The decay is supposed to be 18 milliseconds. However, we can see that the amplitude of this signal is actually considerably lower, and the decay accordingly is on the order of about 3 to 4 milliseconds. If we are measuring the decay based on the 1/10 of a volt denominator. So this clave may be a little quieter than we might have preferred, and that may be contributing to this, although its peak amplitude is supposed to be 150 millivolts, which is approximately correct. So I'll just leave that as good enough. It's a little tiny bit flat, but approximately the correct volume. So this is a high bongo, and this one, we do have the ability to adjust the frequency and the decay time as we do with the low bongo and what's called LC, which low Congo, I guess. So this will be our high bongo, and we'll measure this. We have an amplitude that is about 175 millivolts peak to peak, and that's okay. It's supposed to be about 150. The frequency is supposed to be 600 hertz. It's a tiny bit flat. Measured a couple more times here. Yeah. 579, 577, 576. So how do we adjust this? We adjust this using VR51. It's this one. It's the one closest to the front of the board. And so I'll insert my screwdriver. And we want this to be a little sharper. And so we turn it counterclockwise. And what's that? 507 hertz? There we are, 600 hertz. 600 hertz. That's great. And our decay time is supposed to be 40 milliseconds. So we'll leave that decay time right where it is. In terms of the low bongo, we're looking for, in this case, a frequency of 400 hertz. And we, again, appear to be just a slight bit flat, but not very. We're at 390. Yeah, and we adjust this using VR53. There we are. We just had to break the glue. It's now measuring around 405. 399, close enough. The next measurement is our low Congo. And this is supposed to be 208 hertz. So let's see what it is. We appear to have about 200 hertz. And we have a peak to peak around 0.4. So it's a little on the louder side. And we'll adjust this slightly. First, let's get the frequency right. It says it's now 128, 197. Yeah, we're getting about 195. And so we might like to increase this ever so slightly. And we do that with VR55. Okay, so VR55 is this guy right here. And if we want to go slightly sharper, that's 210 or 201, 203, 205. We're looking for 208. Okay. 206, 207 and a half. Gosh, this is a little touchy. 208, there we are. We'll leave it at that. And we're looking for a decay time of about 150 milliseconds. And I'm going to take that as being from the peak to peak of 212 to the peak to peak of about 20. And in order to see this properly, I'm going to decrease this, and a peak to peak of around 20 would bring us to about 107 milliseconds, and we're looking for 150 milliseconds, and this is adjusted using VR56. So to extend this, what we would do is adjust VR56. VR56 is right here. This is VR56. And we want to extend this decay to about 150 milliseconds. Oh. Let's have a look at what that is. That's giving us a much greater amplitude and a much, much greater decay than what we wanted. It's very twitchy. Yeah, this is approximately correct right here. So we're looking for a peak to peak of about 30 millivolts as being the cutoff, and that occurs around 150 milliseconds. And so that is a reasonable decay for this drum. So the next adjustment is the cowbell, and similar to a number of other Roland instruments, the cowbell is comprised of two oscillators which are pitched off of one another, a high and a low sound. And the first thing we want to do is measure the high sound. And the way we do that is we connect to the collector, the middle pin of Q529, which is located right here. And we measure the oscillation on the oscilloscope, which is currently at 711 hertz. And we're looking for a frequency of about 800 hertz. And the way we adjust this is using VR67, which is located adjacent to the transistor or very close to it. And by turning it counterclockwise, we increase the frequency, decrease the period, till we get to around 800 hertz. There we are. And then we measure the frequency of the second oscillator, the low oscillator, at Q530, which is just adjacent to 529. And similarly off of the collector. We'll turn off the instrument first and remove this little clip. Move over to that collector on the adjacent transistor and turn the instrument back on. And we see we have a frequency of 530 and we're looking for 555. And the way we adjust this is with VR568, which is, again, very close to this transistor, as it's comprising a portion of that oscillator. So we're for 555, and there we go. Now, if we want to listen to the cowbell, the way we can activate it or trigger it is by shorting Q527 across the collector and the emitter, which are pins 1 and 2. Q527 is the fifth one in this row of 5 transistors. And if I temporarily short the 2, actually we're not hearing anything. You know why? We need to actually turn the instrument on. We need to start it. We need to start the clock. And then as I short this, see? That's our cowbell. Beautiful. And now we want to assess the decay time. Although we can't really adjust this, the way we look at it is, again, we come back to this pin here, and just put this down. I'll put this on single. It's armed. Okay. So that's our cowbell captured, and decay time is supposed to be around 60 milliseconds. And I'm going to say that that's about right. So we can move on to the tambourine and the guiro and the marimba. So the tambourine we monitor from pin 34, which is where we are, and we can only adjust the amplitude, and we use VR62 for that. So we slide our add voice knobs upward. So this is our tambourine. We can turn that down so we don't have to listen to it quite so much. And we're supposed to have about 250 millivolts peak to peak, and I'd say that we're in the right range with that turned all the way up. So that's fine. So we'll leave that where it is. So we're examining the guiro sound, and the guiro has two elements to the sound, a high frequency element and a lower frequency element. And I'm going to play the guiro, and in order to do this, I've selected no patterns. I have the cymbal and hi-hat silenced, and all I have is the volume turned all the way up and the guiro fader turned all the way up. What's described in the service manual is 2 target frequencies for this sound, and they are 125 hertz and 77 hertz respectively. And they are to be adjusted together with VR59. And so I'll play this and adjust VR59, and we'll listen to the difference that makes in the sound that we are listening to. So VR59 is right here, and I'll press play. And you can see as I turn this counterclockwise, we get a reduced frequency. And that's turned all the way up. So what is this referring to exactly in terms of the frequency? What is it that we're supposed to be measuring? This is a portion of the sound that we're looking at here on the oscilloscope. If we look at this with about a 5 millisecond per division time base, we see clusters of tone here. And if we zoom in quite a bit, we see that each of these tones is comprised of a waveform. And the frequency that we are looking for is not the frequency of this actual waveform. As you can see here, the period, the difference between the peak of this wave and the peak of the wave immediately to its right, that period is much less than 1 millisecond. What we're looking for is a period of about 13 milliseconds on the low frequency portion of the guiro sound, and a period of about 8 milliseconds on the high frequency portion of that sound. And what is it about the guiro sound that corresponds with these measurements? Well, if we zoom out and examine the guiro sound, we see that each of these bursts of tone are occurring in a regular pattern. And in this case, we see one beginning here at around 27.7 milliseconds, another beginning around here at 37 milliseconds. So about a 10 millisecond periodicity. And it's this period that we're supposed to be paying attention to when we're adjusting the frequency of the guiro sound. So which is the so-called high portion and which is the low portion? Well, again, if we listen back, we hear a number of low frequency guiro sounds followed by a higher frequency guiro sound. That last sound was the higher frequency. That's the low frequency. High. So again, that ends in the high frequency sound. So if we examine the low frequency sound, we have currently a periodicity of approximately 47.9 milliseconds to 38.3. And so this is a period of about 9.6 milliseconds. And this being the lower portion, we need to increase the period time and reduce the frequency. So we want to increase this periodicity to about 13 milliseconds from burst to burst. So where are we now? We have a periodicity now of approximately 22.6 minus 10.8, or approximately 11 milliseconds. And again, we're looking for a period of about 13 milliseconds. So where are we now? Well, we have a period of approximately 24.8 minus 12 gives us about 12.8. So that's approximately the frequency that we should be looking for in terms of the guiro sound. In terms of the other aspects of this sound, the only other adjustment we have is for the amplitude, and we adjust that using CR-78. We're looking for about a 300 millivolt peak-to-peak signal, and if I adjust the scale here, we can again see that some of these are approximately 0.8, 0.85 volts peak to peak, and all of them are much higher than the nominal 0.3 volts peak to peak. And so we could do well to adjust CR-73 and turn down the amplitude of the guiro sound. CR-73 is way in here next to this integrated circuit. It is the trimmer which is closest, in fact, to this integrated circuit, right here. So according to this, even though I believe I've turned this down as far as I can turn it, and this potentiometer is not moving very freely. It's only giving me about 45 degrees worth of travel. Even though I've turned it down as far as it'll go, we still appear to have a signal that's louder than it needs to be. So I had some difficulty adjusting CR-73, which is this trimmer potentiometer, and this is the amplitude of the guiro sound. And we're looking for about a 0.3 volt peak to peak signal. And if I start the instrument, we can see that we have approximately 0.3 volts peak to peak. In some cases, a little higher than that. We're showing here 350 millivolts roughly of amplitude, but we certainly now have a little bit more control. What did I do? Well, what we had here, and we have this on most of these trimmer potentiometers, is a little bit of glue, which is placed on the potentiometer after the instrument is assembled at the factory. And the glue was actually preventing the potentiometer from turning. So I removed some of that glue. Normally, simply breaking free of the glue will allow you to turn the potentiometer through its full range of travel. But in this case, that was not the case. So let's look at this signal again. And I think that's probably going to be okay. We're set up right now to make some adjustments to the so-called metallic beat. And you don't actually need to listen to this in order to make these adjustments, but you can. And the way that you do that is by putting the metallic beat fader all the way to the top, turning the cymbals and hi-hat off with the cancel voice push button, and pressing start stop. And you'll see that in time with your tempo that you've selected, we have a metallic beat. And that responds to the fader in terms of its volume, but the tone of that doesn't change. And if we take the cancel off the cymbal and the hi-hat, we can hear a little bit of the cymbal in the background. We can add tambourine and guiro and so on. And again, this is without any pattern selected. So I'll just stop that for a moment. What we do is we need to monitor one of three different signals that are coming out of IC 501. And these are to be monitored either on pin 8, pin 4, or pin 10 and adjusted to their appropriate frequencies. We're currently on pin 8 of IC 501, which is located right here. And the way to get access to pin 8 is by attaching to R578, which is a 470 kilo ohm resistor, which is adjacent to IC 501. And you can see on our digital oscilloscope that we're measuring what is basically a square wave. And we have a frequency here of 5.8 kilohertz. And what's listed in the service manual is a target frequency of 6.17 kilohertz. And this is adjusted by VR64. So I'm going to make some adjustments. VR64 is located right here. And by turning this counterclockwise, the frequency decreases. And clockwise, it increases. I've got a range of about from 7.8 kilohertz down to 5.3. Again, we're looking for 6.17 kilohertz. Right about there. That should do us just fine. And the next adjustment is to be made by attaching to pin 4 of IC 501. And that's best accomplished by attaching to R579. And I will turn off the instrument and move my oscilloscope probe. R579 is actually another 470K resistor. It's right here. And what we want to do is attach to the leg of R579 that is furthest away from chip IC 501. And that's connected to pin 4. And when we do this, we turn the instrument back on, we can see, again, we have a square wave, and this time it has a frequency of 5.3 kilohertz. We're to target a frequency of 5.62 kilohertz, and this is accomplished by adjusting R65. 5.62 kilohertz, R65. R65 is right adjacent to 64, and we can do this while listening, although we don't have to. Oops. And for some reason, we now have a very odd signal. Here we are. I think we lost our ground probe for a second there. And again, adjusting R65, turning it counterclockwise decreases the frequency of this one square wave, and turning it clockwise increases the frequency. And we're looking for a frequency of 5.62 kilohertz. So right around there is the frequency that's specified in the service manual. The next signal we want to monitor is off of pin 10 of IC 501, and we can reach that by attaching to R580, which is yet another 470 kilo ohm resistor. R580 is right here, adjacent to 578. I'll turn the instrument off and reattach the oscilloscope probe to the leg of R580 that is closest to IC501. Turn the instrument back on, and you can see here we have another square wave with a frequency right now of about 3.9 kilohertz. The target frequency for this square wave is 4.08 kilohertz. And we'll adjust that while listening to it. The way we adjust it is by changing the value of R66, VR66. And VR66 is this one right here. And again, turning counterclockwise, although this is currently turned all the way counterclockwise, or maybe not yet. Turning counterclockwise reduces the frequency, and turning clockwise increases the frequency. Again, we're looking for 4.08 kilohertz. So that's it right about there. So that's our metallic beat sound. That's how it was designed to sound when the instrument left the factory. And if yours sounds quite a bit different, perhaps these calibration instructions can help you adjust it back to normal. So the last measurement we're going to take is looking at the decay time for the metallic beat. And this is done by moving our oscilloscope probe to our output pin on the voice board. And again, by turning up the metallic beat sound, having no pattern selected, and pressing play, we can monitor the metallic beat sound on our oscilloscope. And what we're looking for in terms of our decay is a cutoff at 1/10 of the voltage, that is the peak voltage. If we look at the positive portion of the waveform, we see it's approximately 200 millivolts at peak. And if we come down to 20 millivolts, we see that that is achieved roughly 58 or so milliseconds after the initiation of the beat. And the target for decay time is 50 milliseconds. So this is really within the range that we might be expecting. And accordingly, this portion of the instrument is working as it should. We should also expect about a 350 millivolt signal, peak to peak. And in fact, we're getting about 355, 345, 370. So again, we're right in the right range here in terms of the amplitude of this metallic beat signal. Let's see how this mixes in with an actual beat, shall we? Well, that's all for this installment in our series of videos on the CR-78. Our other videos feature rebuilding the power supply, building a replacement logic board, and selecting and installing a MIDI kit. I hope you enjoy this series as much as I did making it, and as always, your comments, feedback, suggestions, and questions are most welcome. To all of you out there, take care and thanks for watching.